Alright, welcome back. So, we're about to start question 2. Let's see. So, we're given block A and block B. Two blocks affect the acceleration. Block A has a mass ma, rests on the tabletop, and there's negligible friction, so there's no friction, we can ignore it here. And block B, mass B, hangs off of it. The pulley has negligible mass and spins with negligible friction as well, and the blocks are released from rest. So suppose if mass of block A is much greater than the mass of block B. So basically, let's say that MA was so much greater than MB. Estimate the magnitude of the acceleration of the blocks after release. So what we need to understand when we're doing these types of problems, when there's like a tension between two masses, is that there will only be bear with me. There will only be acceleration when the net force does not equal 0. So basically, if we look at block B, we can see that there's one force on it, and that is its weight, mg, which we'll answer down here in a second. And here we can see the only force acting upon block A is the tension force. And this tension force is equal to its mass times acceleration. And this acceleration is equal to its mass times acceleration, which is equal to its force, which is equal to its weight. So basically, is the force of gravity on, let's say B, let's just write another B, equal to the tension force that block A exerts on block B? Question mark. Here we can see that the block of mass A is, if the block of mass A is so much greater than the mass of block B. So automatically we will know that T is greater than FGB. How do we know this? Well, this M is so much greater than this M. And this acceleration is equal to G because, once again, the pulley has negligible mass and has negligible friction. So this pulley right here will not affect either its mass or acceleration. I mean, it's their force, since it has negligible friction. So we can ignore the frictional force in play here, as well as there being negligible friction between block A and the tabletop, as well as the mass, the string having little to no mass right here. So from that, we can see that G and A, just G is just the same thing as G. Its acceleration down, block B's acceleration down, which is 9.8 meters per second squared, is going to be the same thing here. The only thing that's different now are the M's. So if the mass of block A is much greater than the mass of block B cannot pull this down. It won't be able to pull this down because its M's are different, but its accelerations are the same. So the tension force will be so much greater than the force of gravity of block B pulling downwards that there will be little to no movement. So the magnitude of the acceleration, actually no, I'm sorry, not there will be little to no movement, there will be little to no acceleration. So we'd say little to no acceleration. There can still be movement, but there cannot be much acceleration because remember, F equals A. F equals ma. The masses are different. The accelerations are the same. The tension force is much greater. But what we want to know when it says, when I'm saying little to no acceleration, is that, sorry, let me think about this. Little to no acceleration. So there's no velocity here, which would be the change in distance. The little to no acceleration means the change in velocity. So since the net force in this sense would not be zero, there will be some force, some type of acceleration, but it will not be much, since the only thing that would be able to move this system is this block. And since this block is has so much less force than this block, there will be little to no acceleration. There will be movement, probably not much, but there will be little to no acceleration because remember, F equals ma. The mass and acceleration is the force. So, and once you go back here, the net force is not zero, so there will be acceleration, but it'll be little to none. You cannot say that there is none, because when there is a net force that is not equal to zero, there will always be some type of acceleration. You just have to apply it to the system that you're looking at to make the right choice and the most logical assumption. And that's I. Alright, let's go to B. Now suppose that the mass of block A is much less than the mass of block B. Estimate the magnitude of the acceleration of the blocks after release. So, here, once again, remember, if F net does not equal 0, then A does not equal 0 either. A has some type of magnitude. Sorry, then. So now we're saying that the force of mg, which is this, going downwards, will be greater than the tension force, which is this right here. Whoops. Excuse me. This force right here is the tension. So, and we know that because mg, right, greater than ma. The a and g would cancel out since, remember, the plates are frictionless, the rope is frictionless, so m is greater than m. So mg is greater than mg is greater than t. In this situation, estimate the magnitude of the acceleration. So in the past situation, since block A had so much more mass but was on this tabletop, there was only one force. It contributed more to this force right here, mg. This weight downwards had so much more force. Sorry, not mg for block A. I meant this tension had so much more force than mg, which is why that the F net wasn't 0 and was in the tension's favor, which was why that the blocks barely had any acceleration, was because even though the F nets weren't 0, since the tension was not in since block A was not in free fall, which is what I was trying to say, since block A wasn't in free fall and it had a normal force, right? If these things were switched, there would be a much bigger acceleration, which is what's happening right here. Block B is in free fall, except for there being this. Technically, it's not in free fall, but it's kind of. But there's a tension holding it up. So technically, the block B's force would be mg. Would it be minus t? If it were in free fall, okay. So yeah, ignore what I just said. Let's go back to the problem. If block A's mass is so much less than block B, then this block B would be accelerating at so much greater of a magnitude, because when it has more mass, but it would be accelerating at mg minus t equals ma. You have to say mba. So we say negative, I guess, because it's going downwards. Actually, no, we can ignore that. So suppose the block of mass A is so much less than the mass of block B. So yeah, just block B is going down at so much more, since so much more bigger than of a magnitude than the accelerate at the distance plus rather than block A, because it has nowhere to fall on, and the only thing that's holding it back is the tension. But the tension, remember, since block A is so much less, is very small compared to the mg pulling block B down. So block A will move in proportion with g, with its acceleration, which will be the same thing as the acceleration here. So mg, the g will be the same thing as the a. The g here will be the same thing as the a up here. T equals ma. The only difference being that this will accelerate at so much more of a force, since the situation is different. Block B is falling down at so much greater of a. So its g is essentially increasing as it continues to fall more and more and more as it covers more distance. So this block A will how do I say this? Block A will accelerate because the force will continuously increase since it is falling at so much faster than a rate as it was when block A was much greater, when the tension was holding it back. So this will have a much bigger magnitude. Estimate the magnitude. You just say large. It would be a much larger magnitude, since its g would be continuously increasing as it falls and covers more distance. So its force would continuously increase, which would result in a bigger imbalance in the net force, which would result in a bigger change in velocity, so a larger acceleration. So essentially, this one is smaller since tension is holding the block B back, but this one is larger since block A is not holding block B back. Block B is much larger than block A, so it'll have so much less force holding it back, which will allow it to accelerate continuously at the rate that it'd like to in order to move block A, and to accelerate block A at a much larger magnitude. Sorry if that was a little confusing. I guess you could also say for II that block A is pretty much like, just as much less. It's damn near just like negligible, and the g will just be increasing at its regular rate of what, 9.8, or what do you want to say, 10 meters per second squared. So it'll continuously increase, its weight will continuously increase while as it accelerates. So block A will continuously increase till it falls off and begins to fall at the same rate that the block B does. Sorry. Alright, now we can go to question B. Now suppose neither block's mass is much greater than the other, but they are not necessarily equal. Okay, so underline that. The dots below represent block A, block B, as indicated by the labels. On each dot, draw and label the forces, not components, exerted on that block after release. Represent each force by a distinct arrow starting on and pointing arrow from the dot. So, of course, what I've been saying for like the past 13, 14 minutes, block B has mg. Block B has mg, and so does block A. Every single object which has a mass has a weight. That weight is equal to mg on Earth. And since block A is on a surface, and Newton's third law says that for every action there will be an opposite and equal reaction, the table will exert a normal force equal in magnitude. So let's try to make it equal. about that. Equal in magnitude to its mass times gravity, which is its weight, pushing down on the table, which is why the block stays where it stays. And it does not go higher, it does not go lower. Block B has a rope tied to it. And what is this rope? It is tension. So let's just make this like that. I don't think for these two that the length necessarily matters because we don't know the length of the the magnitude or how much mass either block has, which doesn't matter. They're not necessarily equal, but they're not much greater than the other, so we could say it's a little bit equal. What the heck was that? Such out a drawing for no reason. There we go. One more thing, which is what I drew here. Block A has a tension force. So these are all forces. These are not components, which would, for example, be like velocity or something. These are all forces that are acting upon the two blocks. And remember, the string exerts the tension force from the block A onto block B, and block B exerts the tension force through the string on block A, which is why they stay in a pulley like this. That's why there is a T. mg is universal for all objects with a mass, and the normal force is here because the table exerts an equal and opposite force onto, and here I can write it, Newton third law. For every action, and you could just say force, comma, there exists an equal and opposite reaction. In this situation, the mg exerted, the weight exerted by block A onto the tabletop. The tabletop exerts the exact same amount of force back onto the block, which is why the block does not go above the table and does not break through the table, because the table has enough force to push back with a certain amount of normal force. And yeah, that's question B. Alright, let's keep going with FRQ number 2, and let's read number C, letter C, problem C. Sorry. Fine, okay. Derive an equation for the acceleration of the blocks after release in terms of MA, MB, and physical constants as appropriate. If you need to draw anything out other than what you have shown in part B, to assist you in the solution, please use the space below. Do not anything to part B. Okay. So we want to derive an equation for the acceleration of the blocks after release in terms of these two and physical constants and stuff, which I doubt that we'll need, but we'll see if it comes up along the way. So let's write the forces, the sum of the forces for each block. So for, let's say, mass A, let's say the sum of the forces for mass A is equal to just tension. If you remember, all there was mass A here was B, and it was on a table. Like that. This is the only force acting upon it. So this T is the sum of the forces for block A. But what T also equals, if you remember Newton's second law, F equals ma. So T is equal to m, mass of A, times acceleration. The sum of the forces, so that's sum of the forces for mass A. There's only one force at play in the horizontal direction here, which is the tension. So we know that the force that will be pulling down on A is the tension force. It will only be the tension force pulling down on it. But there is also a force that, let's say, that makes, without this force, there would be no tension, essentially. And that is mass B's mg. But what we have to remember is that since there is a tension right here, there must also be a tension right here in order for there to be a tension existing at all. So there's mg and t, and you want to know its force going down. Mass B, the sum of the forces, is equal to mbg minus t. And I'm sorry, I forgot to put this here. Remember, F equals ma, so we have to add the a there. So from what you can see, the mass times the acceleration is the force and becomes the sum of the forces. So we want to find acceleration. This right here. This right here. This is what we want to find. So we already know we already know how to find the acceleration here. It's just m mass times a acceleration. We already know this. But here we want to find it in terms of ma and mb. So how do we do that? What is the tension? Oh my gosh, it's equal to something here. ma times a. mba is equal to mbg minus t. What is t equal to? T is equal to, where's my mouse? Here it is. M-A-A. So what we want to do is that we want to get A by itself. Alright? So the way we get A by itself is by putting it on one side. So let's add mass times mass of block A times A over here. So we get mass of block A times A plus mass of block B times A equals mass of block B times G. So we can factor this out. We get A MA plus MB equals MBG. And remember, we want to get A by itself. So we divide it. I'm going to go back up here. We divide this by MA plus MB. So we get A is equal to MB over MA plus MB times G. So this is our equation for acceleration. It's in terms of ma, in terms of mb, and a physical constant of g, which is 9.8 meters per second squared. So that is how you derive the equation. Essentially, you make two separate sum of the forces for both masses, and you just put them together and you solve for whatever they want you to solve, which in this situation was the acceleration. What you also have to keep in mind is that there honestly was no point of doing this, and since the only point of doing this was because they asked you. You know that there's no friction here? There's no friction going this way. So you just cross that out. The string has no mass, the pulley has no friction. What does that mean? It means all the forces are conserved and no energy is lost in this system, which means that the force is conserved, which means that this MA is equal to this mg, because this mg is the one that's forcing it down, so this A has to be equal to this g in order, since there's no friction or anything happening to it or acting upon the system. So these two accelerations are the same. I think that's all for C to remember. So, it seems that I made a mistake when I was explaining the deriving an equation. So, remember what I said of t equals m, I'm just going to say 1 for a, t equals m1a, and m2g equals, m2g minus m1a, which remember is the tension, is equal to m2a. So you add that, right? You add m1a here. So it's just m2g equals m1 plus m2 multiplied by a. So what I meant to say here was that these a's are essentially the same. Why are they the same? Because the only force that's pulling them both is the tension. The m2, the weight, the force of m2 times g minus the tension is equal to its mass times acceleration. And its mass times acceleration for m2 will be the same as m1 because it's m2a that is going downwards will be what is pulling the mass 1 horizontally. So I just wanted to add that to C to make sure that you understand that since these two accelerations are the same and that this A and that this G are not the same unless we go back to where in part what part was it? Part A per here. Part A double I where mass A was much less than mass B. That is when mass 1's acceleration will be the same as mass G since its mass is pretty much negligible. That's just what I wanted to add, that these two accelerations were going to be equal since they share the same tension force. Alright, let's see what D is asking. Consider the scenario from part A double I where the mass of block A is much less than the mass of block B. Does your equation for the acceleration of the blocks from part C agree with your reasoning in part A? So remember what we got from part C was that it was A equals m2, which is B, m mass block B, over m1 plus m2 times G. So essentially, A is equal to this. And this A is supposed to be, when you think about it, here, I'll show you. Let's draw it. I think drawing will help us. Here's mass, there's 2, here's 1, and this is the table. So if this mass is so small, there will be such little tension that is pulling up on this. There will be much tension pulling up here. Way more. Why? Because this mg is so much greater than the tension here. The tension pulling down, okay, that was wrong. That's completely wrong. The tensions are the same throughout the entire thing. What I was trying to say was that the mg will pull on this, will cause the tension force on the mass 1. That's what I meant. The tension force on the mass 1 will be so much greater than the tension force on the mass 2, since mass 1's tension is so much more smaller than the mass 2's since the tension pulling on mass 2, since mass 2 has so much of a greater mass than mass 1. So T equals m1a. The m is extremely small, and the a will be essentially the same as G. And why will you might be wondering, okay, why would these two be essentially the same? Well, if m1 is negligible and all you have is acceleration here, what is and you know that acceleration, oh, you can't see that. So what I was saying was you have the acceleration here. Let's just write it down. m1a equals m2g essentially, because the tension, there's barely any tension force since m. So if we consider this negligible, we can say that A equals F over M. We know this also, because remember, F equals ma. The force is this. So A equals m2g over m. These two cancel out. All you're left with is A equals g. So essentially, this A and this g are essentially the same when block A's mass is negligible, because this is essentially the only force that's acting upon it. This is essentially its new force. This is the tension force now. Essentially, there is little to no force pulling up on the mass 2. So mass 1 and mass 2 are essentially part of the same. They are part of the same system, but they will be accelerating at essentially the same rate since mass 1's mass is so small that its tension force pulling up will have little to no effect on this force, which will cause the F net. Where is the F net will be so much more greater than 0, to the point that m1's acceleration will just be equal to the acceleration of gravity, essentially, and soon it will fall off and accelerate down at the same rate as block 2. So does your equation for the acceleration of block from part C agree with the reasoning in part A? So let's put this into here. G sorry about that. I was thinking for a second. So m1 is negligible, imagine, right? Because here it's much less. So what we have here is A equals m2 over m2 times g. These cancel out, and all we're left is A equals g. So we got the same thing here using this way, but using this equation we get essentially the same answer, right? Acceleration is equal to the acceleration of gravity, since m1 is so small compared to m2 and mg. And yeah. Alright, let's do the final problem, E. So, actually, did we finish D? According to your equation, the acceleration becomes for a certain value and ma. Oh yeah, we explained that. So let's go back to E. While the blocks are accelerating, the tension in the vertical portion of the string is T1. Yeah, so there's M2 here, and remember there was T1 pulling up. So the pulley of negligible mass is replaced with a second pulley whose mass is not negligible. When the blocks are accelerating in the scenario, the tension in the vertical portion is now T2. How do the two tensions compare? So I think let's make the diagram again. So this pulley now has some type of mass, and there's a block, some type of tension on it. Here's M2 and the M1. And the question is, how do the two tensions? So let's say now we have T2. This is going to be the one with the pulley that has a certain mass. The mass is not negligible. So essentially, this is still T. So now M1 sorry about that. So to understand this problem for myself and for you, let's go back. So let's say that this is just the regular pulley with a massless pulley, So this is M2. Gosh, I really can't write M's. This is M1. So here, basically, we can say that if these two blocks are accelerating, then this then this force is going to be greater than the tension force. There's going to be an F net that is not equal to 0. Basically, this M2G is going to be greater than the tension. Right? That is the only way that it can accelerate downwards. That is the only way, remember? Remember I wrote earlier that if F net does not equal 0, then A does not equal 0 as well. So let me clear that real quick. Delete. So, what can we do with that information? Well, the thing now is that, let's imagine if the pulley now has, let's delete this, mass. So the pulley has mass now. What happens? Well, let's get a close-up on the, oh, whoops. Let's get a close-up on the pulley. So I'm going to make two pulleys. This is mass equals 0, roughly 0. And this is mass equals a number that is greater than 0. Alright? So when an object has an acknowledgeable certain amount of mass, it will also have a certain type of inertia, which is Newton's first law, which states that Newton's first law. Newton's first law of inertia states that an object that is in motion, this is not straight from the quote or straight from the writing, this is just a brief summary. An object that is in motion will continue to stay in motion unless acted upon by an external force. Sorry, something's in my eye. So basically, let's say you're in a car. Sorry, I don't know really how to draw a car for some reason. Here we go. Here's the wheels. And you're right here. And you're moving, and then suddenly you hit the brakes. And the car stops. Let's say you're moving at 60 meters per second. If you're wearing a seatbelt, your body, let's say this is you inside, your body's going to go this way. Your body's going to keep going that way. But the seatbelt that's around you will stop you from going that way, but you'll move forward a bit and then move backwards. So essentially what's happening is that you are moving 60 meters per second as well, since you are inside of the car, right? And a sudden stop in movement, will cause you to stop as well. But right before you stop, there will be a moment where you are still moving that 60 meters per second, but that seatbelt will lock and push you back and keep you to be the same, to be moving the same speed as the car that you're in. The car will also experience this type of inertia. And what I mean by that is that you'll move forward and then move back. Why? Because your body is still moving in that 60 meters per second motion. But when you come to a sudden stop, your body will continue to be wanting to move in this direction. But since a car has stopped moving that way, you will also stop moving, and you will come to a sudden stop of 0 meters per second squared. It's not 0 meters per second squared, it's 0 meters per second. You won't be moving anymore. So basically, once again, an object that is in motion will continue to be in motion. You'll continue to be in that 60 meters per second speed unless acted upon another force. That seatbelt will basically stop you and you'll come back. So that's basically what inertia is. And That's why that an object, also a heavy object, that is not in motion will be really hard to get in motion. But once it is in motion, it'll be really easy to keep it in motion. But it'll be harder to stop it. So inertia is proportional to mass. How do you draw it? It's like this. The greater the mass, the greater the inertia. The lower the inertia, the smaller the mass. And basically, that's just a quick rundown of what inertia is. And I'll show you how it runs into what rotational inertia is as well in just a second. All right, rotational inertia. That is what we're going to be talking about now. So if this pulley has a certain mass, there will also be something called rotational inertia, which is basically just inertia, but just in a circular movement. So this is, let's say I is inertia, and there's an inertia, and there's also mass 2 here. There's also tension, and there's mg. Let's label these. So basically, now there's not just a tension force, which will be lowering the acceleration of the mass. There will also be an inertial force lowering the acceleration of the mass. So now, mg minus, you would write t plus I equals ma. You'd write m2 here to signify it. But essentially, yeah, this is pretty much it. So it doesn't tell us if we are saying this in the scenario of when block A is much less or when block A is much more than block B. But since here they signify that when the blocks are accelerating, I'm going to just assume that we're talking about when block A is much less than block B to make it much easier, so that the acceleration will be the same and that the tensions won't be the same as well. I forgot to say that. The tensions will not be the same for mass 1 and mass 2. And you might ask, why will they not be the same? Well, that's just because it says rotational inertia. They'll need some type of force in order for the pulley to start moving, and that force will be lost, and that force will be used for the inertial force and will not be used for pulling down on the will be lost in the act of pulling down and canceling out this inertial force or rotational inertia that is required for the pulley to move downwards and for it to accelerate, essentially. So what does that mean? That just means that there will be more acceleration. There will be less acceleration when there is a pulley in the mass. So that just means that since there will be a lower acceleration, so let's say A2 for A scenario 2 will be less than A for scenario 1. So what does that mean? That just means that this right here is greater, right? Because remember, this is scenario 2 with there being rotational inertia because of the mass of the pulley. In scenario 1, if you remember, there was just m2g minus t equals m2a. But now, since we have inertia, there will be a greater amount of tension acting on m2, which will lead to a lower acceleration. So these two will cancel out, essentially. You just get the acceleration is not going to be g anymore, since g will have to be subtracted from this. So the total force minus the tension plus this new inertial force because of the mass of the pulley will lower in a lower, so this m2a, we can say m2a of scenario 2, we can say s2 is less than s1 of m2a, because there's less force going upwards and more force going downwards. Here, there is still more force going downwards, which is why because the F net is not equal to 0, and so that means that it's accelerating. But since, where's my mouse? Here, there's a rotational inertia added to the tension, which means there will be more tension compared to this. So this one will have more force, essentially because of more acceleration. the acceleration will be less in scenario 2. So we will say that the tension in scenario 2 is much greater than tension in scenario 1, because this is basically equals the entire tension. So T1 equals T1, T2 equals T plus I. That's basically what it is. And that is why T2 is greater than, what the heck was that? That is why T2 is greater than T1, and that is how you answer question E. And that is the end of AP Physics 2019 free response question number 2. Thank you.